My name is Christopher Brugnoli. My mentor was Dr. Soper Gordon, and I'll be talking to you guys today about factors that affect animal behavior response to drones. So first off, we need to define behavioral studies. So a behavioral study is usually when somebody goes out into the field, observes and documents animals' behavior. Usually we try and go for a more natural behavior of whatever the animal does without humans or any other extra variables, in a sense. We usually use this in, for example, zoos to compare what their natural behavior is and try and get their captive behavior as close as possible to their natural behavior. So we kind of first started off with usually using binoculars or long-range lenses on cameras to look at and observe animals in the wild and document them. Kind of throws a couple variables, unfortunately, if they spot us. So we got new and better technology, and we started using game cameras and just other video recording devices. These things we usually can put on trees or anything and observe and monitor animals coming into the area or whatever their behavioral response is in that area. Satellites are most of the time used for migrations or bigger animals in a little bit more open areas, such as elephants or whales. And drones are the newest, tool to use for biologists to observe animals, which you can easily just fly these guys over, put either a camera or video recording device on them, and they can get the job done in a very wide-ranging area. So, with behavioral studies, you don't want to be the panda. Panda's the worst guy to be because he's not very good at hide and seek. He needs to get better at his job. Being a scientist and trying to study animals, this is definitely not what you want. It throws in a lot more behavioral changes to the animals because they definitely know, for example, this panda is definitely right there. And they're going to change their behavior based on that. And then whatever you're looking at the animal for, everything is skewed, and it's just not good. What you want to be like is this professional toad over here. You can barely see him right there. That's more or less what you want to be doing, at least if you're going to do any of these studies, is not be seen, in a sense, so that way the animals aren't changing their behavior because they know you're there. So, with drones, there's two different types of drones. The plane style or fixed wing drones are on the top, and the rotary style drones are on the bottom. So both styles have kind of their ups and downs to them. The plane style drones usually tend to be able to fly a lot farther on a charge than the rotary style drones. Also, if one of these engines goes out that they have, they usually can glide to the ground pretty gracefully and not really get injured or damaged too much. With, unfortunately, for example, the 4-rotor drones, if one of those rotors goes out, it's most likely falling to the ground and you're going to have to pay another $4,000 to replace it. But the upside to these guys is they make a lot less noise than plane style drones. The rotary style drones tend to usually make a little bit less noise. The other upside, though, is you can up to the 6-rotor drone. 6-rotor drone, unfortunately, makes a little bit more noise than the 4-rotor guy. But the 6, if one of these engines goes out, it's still flying. There's just going to be a little bit off kilter. So, goal of my paper is to create a standard for drones. What I kind of want to do is be able to plug in, say, for example, intelligence, and get a baseline intelligence number, plug it into an algorithm, and then it spits out a height to fly a drone over safely over an animal. So, my base methods for this paper was to pretty much look at Google Scholar, NCBI, Bio1, and Mars Hill University database. Most of the keywords that I looked at were pretty much drones, rotary style, plane style. Also looked at behavioral studies or behavioral differences in animals, stuff like that. And I also tried to find safe heights, which are pretty much heights that the animal showed no behavioral change when the drone was flown over them. So what most of the times happens when a drone is flown over an animal, they show one of three different responses on average. So a movement response is usually like a flee response. We fly a drone over the animal, and the animal runs the exact opposite direction. We really don't want that behavior to happen because we're startling the animal, it's changing behavior, and that's not really safe to do. Vigilance response is a little bit safer, but we still don't want that to occur. And a vigilance response is pretty much an animal looks at the drone and they know it's there. So it's changing behavior, and we really don't want that. No movement response, like this bear here, is what more or less we want, to show that the animal is showing more natural behaviors, or they're not moving at all, to where they're not showing any impact to the drone. For example, to probably make this a little bit easier to understand, we'll take this elephant. And say an elephant, we throw a drone, we fly over 200 meters above him, and he moves and runs the exact opposite direction. So, since we're trying to find the safe height, what we'll do then is maybe go 250 meters above him. And we might get a vigilance response. So he's looking at the drone, he knows it's there, but that's still not what we want. So we fly it even higher, and say we fly at 300 meters. And he shows a no movement response. That's the response we don't, or that's the response we do want. And 300 meters would then be documented in a sense as the safe fly height to fly the drone over top of the animals. So I wanted to look at more intelligence of these animals. And unfortunately, intelligence is very hard to either get numerically or look at in general. Most of the animals that we usually look at intelligence with, we usually use studies that give them puzzles or other things or brain teasers or challenges to do, and then we say they're intelligent if they solve them. Unfortunately, there's not a lot of papers on the wide range of animals that I kind of looked at, so I couldn't really document or use that as a way. I tried to look at instead was maybe brain mass as a way, which brain mass usually means a bigger brain tends to be a little bit more intelligent, but unfortunately all the animals I looked at didn't have all their brain masses like on point. So I tried to look at neuron numbers, and unfortunately neuron numbers was also really hard to find all the data for, and I couldn't find a complete set for all the different animals I looked at. So that was also a no-go. So I then looked at brain or body mass and as a way correlating that to possible intelligence. So usually on average, if an animal is larger, they have a bigger brain, which tends to mean that they are a little bit more intelligent. Say, for example, the elephant, very big animal, and also a very big brain. And we also know from studies that they usually tend to be intelligent. So I looked at a wide range of animals, like I said. I looked at, for instance, some elephants, giraffes, zebras, gazelles, kangaroos, crocodiles, alligators, penguins, bears. Very wide range of animals I tried to have in my study, in a sense. That way I could look at a lot of different things. So the first thing I kind of looked at was meters that we had to fly over and compare that to the body mass or the poundage of the animal. So elephant is kind of far out there, as you can kind of tell, and I found out zebras actually were very much affected by drones and very startled. They usually had to be, or the drone had to usually be flown about 350 meters or so above them to get a no response out of them. And then penguins, most of the birds, alligators, crocodiles, they usually tend to be a little bit lower on here, which I wanted to see if that was actually the case. So I did another test, and I did a ANOVA. Found on average mammals were around 130 meters. You had to fly a drone over to get a no response out of them. Reptiles were around 42 or so, and birds were around 58. And as you can kind of tell, Mammals were definitely a lot higher than in comparison to the birds and reptiles, which is kind of what I thought with the other graph, but I wanted to look a little bit more into this, so I also wanted to compare drones. Fixed wing style drones, as you can kind of tell, they're a little bit higher, and I partially conclude this to be because they usually make a little more sound than the rotary style drones, which kind of makes sense then going downhill. The 8 rotor is the next noisiest. The 6 is only lower because, unfortunately, there wasn't a lot of papers using 6 rotor drones, and that's my conclusion for why it's most likely a little bit lower than the 4 rotor drone. But as you can see, rotor drones are still a lot lower than the fixed wing drones over here. So I wanted to look even further into this and compare all the rotary style drones to the fixed wing drones. So on average, fixed wing drones had to be flown around 220 meters, and on average, rotary style drones had to be flown around 50, which is a drastic difference on average for the amount of the height we had to fly drones over the animals for. I ran an ANOVA with this and found it was statistically significant. So that was actually very interesting finding that out. And I attribute it probably to the amount of noise that these guys make in comparison to the rotary style drones. So most of unfortunately, the data for the fixed wing drones were African animals and mammals, which kind of all came from the same paper. So I would need a lot more data points next time when I would do this study again. Just a couple downsides with it. My future notes, though, are apparently you can modify drones to where their engines make a lot less noise. So I'd probably recommend that for future with anybody that's going to do more studies with drones. To look also into cardiac response is another thing. So 2 of the papers that I looked at, they actually had, for bears and penguins, they flew over the drone. They showed no behavioral response at their heights, but they found out that they had an extremely high spike in their heart rate. So it's something to look into for the future with the drones and studying. For birds, they found out that launch distances made a really big impact in startling them. So plane style drones unfortunately usually need a launcher of some sort, or you throw them. The launchers make a lot of noise usually, so it's going to startle the animals in the vicinity. The birds usually tended to need a launch radius of like over 100 meters or so on average, so you need to be very, very far away to launch a plane style drone. The rotary style drones needed a lot less. The birds didn't necessarily care as much, so that's another thing to look at. Mammals tend to need a higher flying height, and rotary style drones would be definitely a recommendation for the future since they make a lot less noise, and you saw before that on average they could be flown a lot lower. Also, somebody figuring out a standard for all of this, or a standard in any way, to look at the animals would be great. Also, we would have to keep flying drones over many different animals to properly actually be able to use this as a tool for the future. So that's another thing to think about. So I'd like to thank Dr. Zinna, Dr. Soper-Gordon, and Dr. Gilly for helping me with this and all the data of this. And I'd like to thank Amber Tolles, Madeline Bowles, and Taylor Brower for helping me figure out what to talk about and what more to put into this. And here are my references. And yeah.